Okay, we're going to start chapter 8, section 8.1. Specifically, we're going to talk about sequences. So we're going to begin by just kind of defining what a sequence is. We're going to just spend a lot of time kind of getting used to writing out the terms, coming up with a general term of a sequence, and then we'll get into some convergence and divergence of a sequence. So first of all, recall that the set of natural numbers, when I teach this in basic algebra, I say to them, think about how you naturally count. So your natural numbers are the ones that start at 1. So 1, 2, 3, kind of how you naturally count. So we mention this because a sequence is a function, we can think of it as a function, whose domain comes from the natural numbers. Either all of the natural numbers, if we're talking about an infinite sequence, or maybe just a subset of the natural numbers, in which case it would be potentially just a finite sequence that we're looking at. So, for example, suppose we just wrote kind of like a function, a of n equals 2n plus 3. So if I was just to investigate this a little bit, I could just think about evaluating my sequence, subbing in 1, so 2 plus 3 would be 5 here. And then I could think of a of 2, and so 4 plus 3 would be 7. And then I could sub in a of 3, and so I would have my 6 plus 3, which would be 9, and so on. A of 4, and subbing that in, we'd have our 8 plus 3, which would be 11. So what we're seeing in terms of the sequence is we're really getting the values here, 5, 7, 9, 11, and you can really kind of get a feel now. We're just looking at all of the odds, obviously starting at 5 and going on from there. And so the difference too, if you were going to think about maybe graphing this sequence, is it's just this set of points. It's not going to be the entire line of 2n plus 3. It's just going to be starting at 1, so maybe not drawn to scale, so maybe at 1 here, we plot our first point at 5, and then over at 2, then we get our second point, so then maybe that's where 7 is. So it's just plotting these singleton points, and then when we sub in 3, that's where we're plotting our 9, and so on, right? So it's just these singleton values that we're getting if we were to plot the sequence here. And so obviously that would kind of I'll just put a little dot, dot, dot up there, but that would continue. So when we look at this sequence, it is like the graph of this line, but of course the main difference being it's not all of the real numbers in the domain. It's just looking at the values that we get when we sub in the natural numbers. So typically though, we're going to move away from this and we're not going to be using function notation. So what we're going to do is, instead of calling it a of n, we're going to call it a sub n. But you always want to think about, anything you know about the function, like here, I know that that is a linear function. It has a slope of 2. And so as we kind of think about those things that we already know about the function, yeah, you know those things maybe about the sequence. So here we had this kind of rate of increase. We're going for every additional 1 in the natural numbers, the output was increasing by 2. And that really kind of comes from the idea of that linear slope. We go up 2 over 1. So for every increment of 1 we move to the right, we were going up 2. So we have these ideas that we already know from functions, but now for sequences, we're only looking again at the values we get when we sub in the integers, positive integers, the natural numbers. So what we're going to start to see then is a sub n is what we use for sequences. And a lot of times, though not always, there is some variation here. Sometimes it's written in curly brackets, sometimes not. But that's what we're going to see then when we're referring to a sequence. So if I was going to look at the first 3 terms of a sequence, I just have to know that my first term is going to come from subbing in 1. So 1 cubed over, and then 5 minus 1, of course, would be 4. So our first term would just be 1/4. And then we'd sub in 2. So my 2 cubed would be 8 over 10 minus 1 would be 9. And then subbing in my 3, so 3 cubed would be 27 over 15 minus 1 would be 14. And so those would be my first three terms there. So I just chose to just kind of write them out. If you wanted to refer to them specifically, that would be with subscripts a sub 1, a sub 2, and a sub 3 is what we just found there. All right, so now we're going to look at the first three terms of two different sequences. And so the first one is negative 1 to the n, so this is a sub m. So if I'm going to look at, so for my a sub n sequence, and then we're going to have something really similar, we're going to look at a sequence b sub n. All right, so in a sub n, if I start, and I suppose maybe I should use my subscripts here. So a sub 1 is going to equal negative 1, remember we start to the first, and then times 2 minus 1, so of course that's just going to be 1. So negative 1 to the first is just going to be negative 1. So we start at negative 1. All right, then we go on to a sub 2. So a sub 2 is going to be negative 1 now squared times 2 squared is 4. 4 times 2 would be 8. And then 8 minus 2 is going to be 6. So my second term here, a sub 2, well, negative 1 squared would now be positive, and so positive 6. And then we go on to a sub 3. A sub 3 is going to be negative 1 to the third. And then we're going to have times, well, let's see. 3 squared is going to be 9, times 2 is going to be 18. And then 18 minus 3 is going to be 15. And so a sub 3, negative 1 to the third would be negative 15. So there's my first three terms for the a sub n sequence. Now let's look at b sub n. So of course the only difference is going to be we have that same binomial. So as we look at b1 and b2 and b3, we got to go back and look at those powers, but what's in the binomial would be the same. All right, so what's going to happen with b sub 1? We're going to have negative 1 raised to the 1 plus 1. So that's going to start off squared. When I go to b sub 2, I'm going to be at negative 1 to the 2 plus 1. I'm going to be at negative 1 cubed. When I go on to b sub 3, I'm going to be at negative 1 to the 3 plus 1, so negative 1 to the 4th. So what's going to happen here? Negative 1 squared is now going to be positive 1. B sub 2, negative 1 cubed is now going to be negative 6. And then b sub 3, negative 1 to the 4th is now going to be positive 15. So what we want to really observe here is the difference in between, well, first let's just observe one thing, that negative 1 raised to the n, or negative 1 raised to the n plus 1, gives us those alternating powers. What was different here is if I start with negative 1 to the n, that means I'm starting at negative 1 to the first, and so I alternate negative and then implied positive here, and then negative, right? So I'm alternating, but I'm alternating from negative to an implied positive and then back to negative. If I have the factor of negative 1 to the n plus 1, that one also alternates, but since I start at negative 1 to the second power, I actually start off positive, and then I alternate negative and then back to positive. So they're both alternating, it's just one starts negative, the other one starts positive. All right, let's look at a couple of these in reverse. So we're going to come up with that a sub n, that general term of the sequence. So remember, sometimes you can see the pattern, but we want that kind of general formula that would allow you to find the 100th term without going through the first 99. So hopefully on this first one, we're starting pretty, I think, nice here. And I think most students would recognize that we're looking at dealing with the cubes here. And so as we take a look at that, it becomes, sorry about that, it becomes pretty clear that our sequence, a sub n, If I start at 1, that's how sequences are defined. I'm looking at n to the third. So that is my general nth term for that sequence. All right, part B. Well, first let's deal with the alternating, and let's kind of go back up and take a look at, we want the alternating that starts positive. So which one was that one? Okay, that was the yellow one. So I want to start with -1 to the n plus 1 because I want to start at a second power. So I want to start then positive, so I want to have a -1 to the n plus 1 because that means I start at -1 to the 1 plus 1, so -1 squared starts me positive. Now what I have is I have e to the evens. And I'm going to make a little note here off to the side because you're going to often see the evens or the odds. So we're coming up with a few things right here that you're going to see a lot. Alternating, and then now representing evens, or, and then we'll also talk about representing odds. So when you think about how to get 2, 4, 6, 8 out of subbing in 1, 2, 3, and 4, well, that's just 2 times each of those values, right? So what am I saying here? I'm going to erase this here real quickly. But you're thinking about it kind of from the domain idea that you have to sub in 1, 2, 3, and 4 in order to get to the evens, which are 2, 4, 6, and 8. Well, how am I going from here to here? I'm just taking 2 times each of those input values. So 2 times n is how you're going to represent your evens. So if you want to represent the evens in a sequence, 2 times n is what would get you a sequence of the even numbers. And then if you think about that, if you're at the evens, if you're starting at 2, and instead you wanted to start at 1, you could take each of those evens and subtract 1. And so instead of being at 2, you'd be at 1. Instead of being at 4, you'd be down at 3, and so on. So 2n plus 1 would get you all of the odds. So just a little note, because those will often come up. So now what we have, -1 to the n plus 1 times e to the 2n. And again, write those out, expand them, double check that you're getting all of your appropriate terms, and we are. All right, so this next one would be kind of fun if we were sitting in class to, and honestly, this would be something I'd give you to kind of think about some of these. The first two come first one comes pretty quick, second one maybe a little more slowly, but still pretty natural. This one sometimes takes a while because you see the alternating, but then you see the zeros in there. And so this one sometimes takes a while. And, maybe pause and play around with the numbers, see if you can get it for yourself. But one thing that I might encourage students to do on something like this one, because it often prompts them there, is if I said to you, let's just, as a tool here for a second, let's think about kind of plotting this sequence for a second. So just a really rough plot of this sequence. Okay, so if I start at 1, and then the next term is 0, and then the next term is -1, and then I go back to 0, and then I go back to 1, and then I go back to 0, and then I go down to -1, and so on. If you start, remember how I was saying before, if you know things about functions, we're really just kind of pulling the integer values out of that. So if we kind of look at that, it's like, well, what kind of functions look like that? And we start to kind of realize, well, this kind of looks a bit like a sine function, or maybe a cosine function, but we start to see that periodic behavior. So when you kind of notice this, let's just even write that out, this periodic behavior might make us think of the trig functions. So periodic behavior might make us think about, the sine or the cosine functions. All right, so let's go back and kind of think about that here. So suppose we thought a bit about sine, and let's think specifically, well, multiples of sine. So how do I start at sine of 0? I'm at 0. And then where does sine come out to be at 1 is at pi over 2. So if I think about sine, this would happen at, so specifically here, we're going to go with sine. So if I think about this being at pi over 2, and then at pi, and this value being at 3 pi over 2, and then over here at 2 pi, I am seeing basically multiples of pi over 2. So these values are coming from 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. It's sine of those values. So to kind of extend that, those are kind of the typical ways that we would write that out, but we could think of pi as being 2 pi over 2, and you can think of 2 pi as being 4 pi over 2. And so really what we have here is n sine of n pi over 2. So my a sub n, and again, check it out. So if you start at 1 pi over 2, you're at 1. Sine of 2 pi over 2, well, that's just pi, you're at 0. Sine of 3 pi over 2, you're at -1. Sine at 4 pi over 2, you're back at 2 pi, that's at 0, and so on. So kind of a different one there. All right, the last one you might be a little bit more familiar with, maybe if you had a stats class. There's another type of number we're going to see a lot, or an expression, if you will, in the sequences and series in this chapter, which are the factorials. So if you've had some stats, you might kind of recognize these. So if you notice, okay, so we have 1 here to start. 2 is equal to 2 times 1. 6 is equal to 3 times 2 times 1. 24 is 4 times 3 times 2 times 1. 120 is 5 times 4 times 3 times 2 times 1. And these are the definitions of the factorial. So the factorial, by definition, is multiplying that natural number times every natural number decreasing by increments of 1 all the way down until you get to 1. So this is our definition of the factorial. So this one, if you haven't seen it a lot, it probably wouldn't occur to you as naturally. It comes up a little bit more maybe in like a probability or a stats class, but in any case, that one is our n factorial. You'll see more of that as we go along.